Good morning, everybody. I'm here.
Good morning.
Good morning. And I have the weather report as usual. Maybe I need to become a better weather woman. But it is a gorgeous morning in Fayetteville. And if you need to get your 10,000 steps in, today is a fantastic day to do that outside. So my name is Ranveer Jung. I'm the founding director for the Institute for Integrative and Innovative Research, and we have said we are going to stop saying the whole thing and just say IQ-DAR. I'm thrilled to welcome everybody here, and today is our second seminar for the spring series. Before I tell you more about our guest today and let me share a little bit about IQ-DAR. For those of you who are new or might be on Zoom who are new, we're still new enough that we talk about this. IQ-DAR is driven by purpose. Our mission is to pioneer solutions to wicked problems. How? Through convergence research. And what do we mean by that? Bringing academic, industry, government, and nonprofit sectors all together to find solutions that will make a positive societal impact. And we want to be able to create and deploy solutions that become available on scale. We obviously want to be the preeminent recognized as the preeminent convergence research leaders for societal impact. And very much so what we're looking to do is also support economic growth and improve the health and well-being of people here in the region, Arkansas, and beyond. There are 5 words that we use to describe ourselves: integrative, convergence, economic development is there, at scale, and societal impact. I say this every time, and so hopefully it's getting burnt into people's brains, which is a topic that we will be talking about today. So with that, I'm delighted to welcome Dr. Cynthia Chestek, and she's coming to us from University of Michigan. I've known Cindy for several years. Yesterday night, we talked about a few things about when and how, and somebody told me that what we learned is how old I am, and that we have a stand-up comic as a faculty member in our university. So that was a lesson we learned yesterday. Cindy got her undergraduate and master's degrees in electrical engineering from Case Western. So that's kind of a link for me. I got my Ph.D. there. And then she went on to Stanford, and then she's a double E all through. Not very often that we see a double E all through coming in. So she's an electrical engineer. She's been on faculty at University of Michigan since 2012. Besides being a professor in biomedical engineering, she runs the cortical neural prosthetics lab. So there it is, the brain and the prosthesis, very much linking to many of the interests that we have right here in the institute itself. And at the same time, she is known for doing some of the work with carbon fiber electrodes. Some of you might recall that we had another speaker last semester, Elise Castanola, who talked about carbon fiber electrodes. So it's an interesting world of how things happen and with linkages that are there. So today's topic is neuroprosthesis for controlling hand and finger movements. I'm going to let her talk about it because I think we are in for a really good big treat. It is a fascinating area. It has been, the neurotech space has just exploded. We were talking yesterday about when neural engineering kind of came into being and what has been happening and how it has moved from things that are happening in the lab to really now seeing multiple companies besides some that you will know of. There are many other companies moving up, in the background that are actually moving forward to getting these interfaces, these biohybrid interfaces with our systems, with our bodies and our nervous systems out into the market. And so who knows what the future in 10 or 15, 20 years is going to look like. It's going to be really, really fascinating. We had an opportunity to do a Women in Science roundtable yesterday. It was wonderful to see the students here. It was wonderful to have the panel members have a very interesting discussion about it. So I'm glad that we did that. That's the first time we did it, Cindy, in conjunction with a speaker coming in, and perhaps that's something we are going to take on as we go on. So it wasn't its first, So So I'm looking forward to having listening this next hour to Professor Chestek. So Cynthia, welcome.
Thank you. Great, thank you very much for that introduction. Maybe I'll just add about the history of neural engineering. You know, we probably have a lot of students in the room. Research can seem agonizingly slow when you're doing it, but if we go back in time about 20 years, neural engineering as a discipline barely existed, and the first brain-machine interface examples were really just coming about right then. So in the grand scheme of things, things are moving very quickly, even though, you know, it takes a really long time to get that experiment to work or that paper to come out. All right, so let me start with my disclosures. These are all just related to licensed patents, completely passive. You know, I don't have active relationships with any of these companies. First two are braining, and the third one is related to prosthetic hand vertical. So my lab focuses on motor neuroprosthetics, and so we don't stimulate the brain very often. We mostly record, and we're trying to get signals from the brain, nerves, and muscles to try to control and restore hand movement. So for example, in the case of amputation, we're usually looking at nerve and muscle signals, and we're trying to control the prosthetic hand. And that's actually very similar to what we do in brain, but we are, you know, thinking there about paralysis, and we're thinking about restoring movement, for example, by stimulating a paralyzed hand. So I'm going to talk through both of that. So my lab basically does three things. I had named the lab the Cortical Neuroprosthetics Lab, and then immediately we started doing lots of other things. So the heart of the lab is brain-machine interface, but we do these other things now as well that are really very related. So I'm going to talk first today about nerve-controlled prosthetic hands, and I'll talk about the new technique. Again, the heart of the lab, I have a monkey lab where we do brain-machine interfaces. And then also, you know, it was about a third, and it's now maybe more like half of my lab. I end my talks with the most science fiction future, which is carbon fiber electrodes. And that enables us to make electrodes that are smaller than neurons and do extremely little damage to the brain. All right. So let's start with nerve-controlled prosthetic hands. People are always telling me that, you know, they got into this field after seeing Empire Strikes Back, and seeing a seamless, sensory and motor restoration of hand movement for Luke Skywalker. But that movie is now 45 years old. So it's fair to ask, why don't we have this yet? So let's just talk a little bit about the fundamental physics of nerve recording are just extremely challenging. Even if you imagine that you have, you know, perfect hardware, you're talking about extremely small, extremely well insulated wires. Is basically what an axon is, and you have this tiny voltage hotspot that you need to somehow get a wire in. And then you need that wire to somehow not provoke a big immune response. And by the way, you're going to need a lot more than one wire to get a good motor control signal. So as a result, I think the peripheral nerve direct interfaces have been much more focused on stimulation, because that works really effectively. And there's, you know, experts, wonderful experts in the room that focus on that. But nerve recording is a whole other beast. And so, you know, it can definitely be done, you know, never say never in engineering. But we've been able to make a lot of progress because my plastic surgery colleagues developed a surgical procedure that can take an amputated nerve and turn it into a muscle. So we call this the regenerative peripheral nerve interface. But if you can remember muscle burrito, that's basically what we're doing. So in the case of an amputation, there is a nerve that goes nowhere. And the surgeon can take that nerve and divide it down into individual branches, which is very convenient because we'd like to separate out those signals, and then attach small pieces of muscle from the same person. And these are very, very small grafts. So there's lots of places in the body the surgeon can get spare parts from. And so this is a pretty straightforward procedure, and it has been done in hundreds of people to date, maybe bordering on thousands, because it's not only really helpful for prostheses, it also gives the nerve a target. And so that prevents what's called the neuroma to form at the end of the nerve. And so just for, preventing and eliminating pain, this is a good surgery to do. And so in the future, you can imagine people, many people are already getting this surgery to prevent pain. And you can imagine electrodes being placed in those same surgeries. All right. So I have one small surgical picture on the next slide. So you can see these are the, muscle grafts. They look dramatic, but they're about 1 centimeter each. And this is an example of a procedure done in someone whose nerves were amputated above the elbow. At that point, there's basically no finger musculature left. So, the entire finger musculature lives below the elbow. And what you're seeing over here is an ultrasound after the surgery. And that is a tiny new thumb muscle inside of that person's tricep. So if we can see it flexing, we know we're going to be able to record nice, large EMG signals from it. Okay. So let me go ahead and play this video. You can see at this point we worked with 4 people that we're very grateful have volunteered to have this procedure done, and there's tiny wires moving through the skin right there. You can see here, this is a 2 degree of freedom control of thumb movement. I'm playing this video first because this is what we get from the actual RPNIs, right? So this is something that would be extremely hard to do without having access to the nerve signals, even in the case of a pretty distal amputation. So I'll play that first. That is very driven by the RPNIs. Every movie I play thereafter is going to be a mix of RPNI signals and other residual muscles that are left. And to date, we have mostly focused on people with transradial amputation. So there is still some finger musculature left. And so what you can see here, there's 3 participants that worked with us for about a year and 1 that worked with us for longer. And we have done a total of 13 RPNI grafts with small intramuscular electrodes implanted. And they give us a mean signal to noise ratio of 41. So for comparison, if you're trying to record from a nerve, you might be really happy to see an SNR of 2 or 3. And so the SNR of 41 also means that there's just a lot of information in that signal. There's a big dynamic range, and you can sort of use differences in voltage firing rates to predict movements much, much better. Okay. So moving on, let me also just give you an example of what these signals look like. So here, this slide is residual muscle. So this is, what benefits do we get by going from surface EMG electrodes on the socket to implanted electrodes? So some muscles, like EPL here, which is an extensor, are decent on, you can record them pretty well on the surface of the skin. So in this case, we have a signal to noise ratio of 22. On the left is, recorded like from a socket. But you get a much larger signal if you implant that electrode. So on the right, from the implantable electrode, we get a signal to noise ratio of 111. So that's pretty good. However, you don't really see the full benefit until you start looking at muscles that are very difficult to record on the surface of the skin. So for example, FDPI is a really important muscle for flexing the index finger. And it can barely be recorded at all on the surface of the skin. So here, with our measurements, we got an SNR of 3, but with our electrode that is implanted directly into that muscle, we get a signal noise ratio of 98. So you can just, AI is great, but AI can only make things so much better than your physically available signals. So we're very, I like to think our algorithms are pretty good, but most of what you're seeing is a massive increase in signal to noise ratio of the signals that we are feeding to our AI algorithms. Okay, so I'm going to first play you a video of what this looks like controlling an animation. So here we're controlling the hand in front and our participant is controlling the hand in back. And I'm showing you a classifier that is classifying 10 different movements that includes all 5 fingers. So I'm playing this video first so that you can sort of see how fast the neural signals are themselves. The prosthetic hand, unfortunately, cannot move that quickly. So things are, fundamentally slow. We've just switched to some faster prostheses. Also, let me admit this is a little bit of a parlor trick because they're not walking around and doing things. Right? And the signals absolutely change a lot when they start walking around and are in different movement contexts. So while we can do, 10 classes, no problem if they're sitting in front of the table, in practice, we do, 4 or 5 movements. Commonly, we do a fist, pinch, point, rest. So that's what she has here. I'll show you a video with active wrist in a second, but that's passive wrist. So you can see she's changing it, but she has, fist, pinch, and point simultaneously. And importantly, here, implantable EMG signals rarely need to be recalibrated. So somebody who's using surface EMG, if they are pushing the limits of what that surface EMG can do, they usually have to recalibrate the system every day and sometimes multiple times per day. Whereas this, she's been using the same parameters for about 2 years. And so, and this is just a paper we published recently on classifiers, being maintained in multiple different postures from day 836 after implant to 1298 after implant. So of course it's hard to do, have a large N for multi-year implants, but as far as we can tell, these muscle grafts are very stable, right? This is the person's own nerve and the person's own muscle, and from everything we've seen, we believe these grafts are very stable, which is, unfortunately very different than nerve electrodes. All right. So more recently, we added wrist movements, and I'll play a video of that in a second. But let me first show you, the difference between implanted EMG, gelled EMG, and what that is sort of a hospital-grade gelled electrode system attached to the arm, much more than you can actually do in a realistic socket. And dry domed electrodes are the kind of EMG that people can realistically wear around every day because there's no gel component, and it's can be there forever. And so, our accuracy, it actually looks decent across all of these, so long as the person doesn't. And so to really reveal the benefit of implanted EMG, the person has to start moving around. So this is the person making a very simple movement, moving their hand up and down as they're making the grasp. And, you can see the implanted classifier signal stays maintained. This is what's actually in socket, and you can see it go from, 60% on a 1 of 6 to, chance. And that's because they're moving. You can see here success rate overall, can they get it into the grasp and hold it, just falls off a cliff for surface EMG when the person is actually moving. In this paper, I just got the email, it is published, and you can see all of this information online. Okay. So as promised, here's the video for wrist movement. So this is sped up by a factor of 2, but you just saw the video without wrist, where you have to make these large body movements in order to turn the hand to make coffee. This is our coffee task. It's a task where we had to come up with something where you needed to use lots of different grasps, because all prostheses testing really involves these very simple things that you can do with open close, and that's because that's most of what prostheses can do today. But this is, you can see there is a fist, pinch, point, and wrist rotation for making coffee. And the addition of the wrist, doesn't damage the ability to classify these different grafts. So you can see here, I'll just let this video play, and it'll switch from using the implanted signals to surface EMG. You can sort of see our setup here. So there's tiny wires going through the skin right there. And then on the socket here, you can see there's electrodes in the socket. So we can record simultaneously from electrodes in the socket and from the implantable electrodes. So I'll just let this play until he goes to the surface control. And you're basically going to see that it doesn't work at all. And I'll point out, this is, no one would walk into an O&P clinic or a orthotics and prosthetics clinic and have them program for 6 different movements, right, using their surface EMG signals. But, for science, we do these comparisons. We ask the person to try as hard as you can, right? But inevitably it doesn't. You can't really do that yet with, or with surface EMG. Okay. So more recent work, which is unpublished, but we presented this at a conference. We are now doing continuous finger movement. So I'll play you a lot of monkey continuous finger movement in a second. But we replicated that with our person on the bottom. And here's monkey data from implanted EMG on the top. And my student, Olivia, has shown that there is no significant change in performance in controlling 2 degrees of freedom continuously when you do not recalibrate the decoder. So, there's, let's see, the light colored lines are recalibrated same day. The dark colored lines are not recalibrated at all since day 1 of the experiment. So, surface EMG must be recalibrated. Implantable EMG generally does not have to be recalibrated. All right, so let me zoom in on what the connector looks like. So the wires go through the skin individually, and they're very small, and that really cuts down on the risk of infection. And under, in this person's daily life, these electrodes live underneath a Tegder bandage, so they can sort of, go about their normal life. But this is obviously not something that people can use at home. So we really need to make the jump to fully implantable systems. My student and my surgeon started a company together. So you can Google Blue Arbor and see some of the progress that they're making. And then another thing that's sort of been a passion of mine for a long time, I'm very, very supportive of this company, but the lack of implantable devices for researchers is a perpetual problem. And I know there's a very creative solution here, repurposing an existing device. And, and researchers are always trying to find something to, existing to repurpose. But a project that I was part of, until very recently, is attempting to make an open source implantable device system for academic research. So at Case Western, it's, the only place that I'm aware of where they have done a fully implantable system, designed, they even do part of the manufacturing at an institution. So there's a website here, cosmic.org, with 2 I's. So, and this system here, it's primarily used for FES, but it has both stimulation and recording modules. It's pretty low channel count and high power, but that's exactly the kind of thing that you can live with for preliminary research studies. And then, this is not a commercial system, right? So this device up here is purpose-made for exactly what they need. It's very low power for that, whereas this is a jack-of-all-trades device, which makes it a master of none. But it's something that can get researchers started. So the project that I was a part of was to open source all of the existing modules and also add new really important features, right? Like a charger anybody can use, a wireless base station, and then my lab worked on a higher channel count recording system for a part of this. So, check out the website. If anything, it's always really fun to peruse through other people's designs. All the design files are currently out there. And there are manufacturers for the different pieces of the module. And there's a new open source company that is sort of acting as a consultant to try to help labs at different schools get up and running with this system. All right, so now I'm going to switch gears to brain-machine interfaces. So let me go ahead and play this video. I guess it's a little dark. But you can see this is an individual with ALS, and you can see it's probably easier to see on the walls. He has two connectors on his head, and those are going to Utah arrays that are implanted in facial motor areas. And this is an individual who can no longer speak, in a way that can be understood by others, but they are reading brain activity directly. And it is appearing on the screen on the lower trace. So he's trying to reproduce the sentence above. So that is brain activity alone coming up with those words. Apologies, there's no sound for the video. And another very important thing, and this is work done at UC Davis, another important thing to know is that they are drawing from a library of 125,000 phrases. They're doing this by decoding individual phonemes and then, kind of applying a grammar correction to get the most likely word from those phonemes given some context of the sentence. But if you want to be an expert watcher of brain-computer interface videos, it's important to note that you can make it look like it's working really well by using a smaller library. I won't call out any labs in particular, but if they were only decoding 50 words, right, and these just happen to be those words, that would be much less impressive. But the work at Davis is true arbitrary English, and this person is using this system to communicate with their family. And so this is the first time that I have seen a brain-computer interface that I think is an actual medical treatment. It needs to go out into the world for people with ALS as soon as possible. And, and it's, and even though, I'll talk about in a second that the electrodes don't last forever, in the specific case of ALS, if you can give a family member 5 more years of useful communication with their family, I think that's something that really is able to go out in the world and help me. And that would be the first. So, all right, so in my lab, we have focused on brain-computer interfaces for motor movements. And I think it's interesting, speech decoding was barely a thing until 5 years ago. And that's mostly because monkeys can't talk. Right? So nobody had any idea how well that was going to work, how quickly that was going to work with just a few hundred electrodes. But the original motivation for restoring movement in people with paralysis. And in particular, when I started my lab, monkeys could basically control computer cursors really well. By that point. So I've been trying to branch into dexterous hand movements. And so we're reporting, we've trained the monkeys to make very precise finger movements. So the monkey, this is a little dark, but we have an animated monkey hand, and it's linked to our monkey's real hands with bend sensors, and they're trained to put their index finger into one target and their middle ring small finger into another target. And from their perspective, they're playing video games for amateurs. So, and if we do our job well, we learn the relationship between neural activity and movement while they're doing it with their real hand. And then we just switch, right? So we're recording brain activity, we decode brain activity into finger movements in real time, and then brain activity starts controlling that animation. And I'll just say that in all the years I've been doing this, I've never seen a monkey freak out by becoming telepathic. They do notice, and sometimes they notice and they stop moving their hands. And they're just like, oh, great, now I don't have to move my hand anymore, right? I can just think and it goes. And yeah, it just doesn't bother them. They just keep going in the task. So let me play first. I'm going to play a video. And first thing that you're going to see here is the monkey doing the task with his real hand. And they are, I would say, much better at this task than people. There's a chart in the lab of how well all of my lab members can do this task and their score, and the monkey beats them by a lot. So they are very fast at doing this. And on the right, what you're seeing is a brain-machine interface control. And this is now an older paper, but we were very happy with this level of performance at the time because that looks pretty good. You know, he can control and do these two-finger movements in 0.4 seconds on the left, and then with brain activity, do it with 0.7 seconds on the right. So what you're looking at on the right is a very, it's got some bells and whistles, but it's a very old-fashioned control scheme. It's a Kalman filter, which is used in, satellites and autonomous vehicles, and is a really common approach for controlling things in the face of noisy data. And so for years and years and years, a Kalman filter, as long as it's sort of done properly, was a really hard act to beat. Even though, since 2004, we knew that, the relationship between brain activity and, the kinematics of movement is not at all linear. And a Kalman filter, there's ways of making them nonlinear, but everybody was using linear Kalman filters. So here in gray, for example, is the monkey's real hand velocity. And in red is the kind of linear estimation that you're going to get with the Kalman filter. And so it, overestimates the prevalence of the middle range velocities, and it's bad at stopping and it's bad at moving fast, right, is what it comes down to. So again, a neural network can immediately, long before 2025, get a really, really good fit to this data. But fitting and machine learning is not the whole story. This is not strictly a machine learning problem. It is a controls and machine learning problem, right? And so when for years, people were developing these neural network architectures and everything looked beautiful, like as long as you didn't try to use it in an experiment. Right? You'd see these traces that are just perfectly replicated, right? Based on previously reported data. So the first time I saw a neural network doing perfect decodes was probably 2012, right? And it just crashed and outperformed the Kalman filter, right? In fact, one of my colleagues was trying real fast to publish his neural network decoder before the next Kalman filter paper dropped because he knew it was going to be so much better, and he wanted like 5 minutes of being a good decoder. So 2022. So this person up here is Matt Wilsey, and he is an engineer and neurosurgeon, and he was in my lab for his residency research. And then we recently hired him as neurosurgery faculty. And he is starting a human brain-machine interface program at the University of Michigan. But during his residency research in my lab, he, got sort of special permission to take machine learning courses, during his residency and things like that. And he implemented in real time what I would call a modern, actually good neural network. It has many fewer bells and whistles than we'd seen in the literature for many years prior. But what it did have is there's a little bit of cleverness on the front end. It's just a convolutional neural network that's actually sort of focused on the not looking too far in the past. That's a way to fool yourself with offline data. So very recent signals, but lets you shift things around in time a little bit. But also what this is just a feed-forward network that is very heavily regularized, right? We are, you think you're not fooling yourself with overfitting offline, but you are, right? And so this is very heavily regularized, and it's actually very straightforward, very shallow. And we would also refer to this as input-driven, right? So it's a feed-forward neural network. It's not going to do anything if you disconnect the input. There's no internal dynamics, right? And it's just a pretty, straightforward, nonlinear fit. And it also got to the point where, in the 2020s, it starts to be really easy to retrain neural network algorithms during an experiment, right? So you can sort of, tweak, mess around, and see what's going on. And this works, we say we were very surprised at how well this worked given the simplicity of the network, right? So now we actually have something that is, neural architecture, nonlinear, and reliably outperforming the Kalman filter. So this is how it works. It's a slightly harder task, so it's harder to see the difference without graphs, graphs and quantitative comparison, but it's got faster fasts, and it can stop. Right, so the extremes of velocity are now good, which is exactly what you want from a nonlinear algorithm, and it works pretty well. And so since then, we have been exploring a lot of other neural network architectures, and they all need tweaks to be used inside of a control loop. So if you look at this paper, this is my students' paper going through and trying lots of offline algorithms in online experiments. And what I'll say is read the details carefully. There's like these single sentences, that were several months of, making this actually work in a control loop. Here we find, and it's been true since then, the LSTM has reliably the highest performance when we test it in an online setting. Higher than the feed-forward network, which is down here, but they're all pretty close. So you can get almost any neural network architecture to work well. My students very sadly have been trying to outperform the LSTM for a couple of years. Transformers, can equal but not beat it, and combined Kalman filter neural network can equal but not beat it. So LSTM is very hard act to beat. And the LSTM, it's important to note, it has its own internal dynamics. So, that's a good and a bad thing. It's a bad thing, so let me play the video because these look amazing. But the key is to note that it will happily memorize your training data for it. So with the Kalman filter, I can, put a couple of targets throughout that space, and I can be really sure it can generalize to hit targets between the targets. Not at all true for an LSTM. If you give it just a small number of training targets, it will just memorize all of them and go straight there, right? So we had to be very careful how we train these networks. But what that means is you can actually control the amount of, whether this is continuous or a classifier, or more like a classifier that memorizes movements on a per movement basis. So what you're looking at here is a neural network, an LSTM, that we have turned into, a classifier for the less well represented finger. And I have forgotten which one of the fingers it is, which is kind of the point. But for one of those fingers, you can move it pretty well, but you can't hit every possible target. And the other finger is truly continuously controlled. And a trick we learned from David Cicillo's papers is that you can actually visualize with a lot of these networks. Did you make a classifier or did you make a continuous controller? And so this has been a really, really helpful analysis trick. I don't know if everybody knew about this but us, but if you PCA a neural network, this one was one that is, turned itself into a classifier. This one was trained on fully continuous data, and it is a continuous controller. All right. So, and I also want to point out here, my student Hisham just did a major service to the field, and he released, he curated and released 303 data sets from our best monkey for years and years of brain data reporting. And so this is now available online. Though I'll point out, so, this electrode array worked from 2020 to 2024. And then basically abruptly stopped. And so you can see from the paper that it was gradually degrading over time, and you need, this much data to see that. But this is now a nice lead-in slide to the rest of my presentation on electrodes in a second. I'll briefly mention, where are we going next with this is, as the decoding and the devices are moving towards human experiments, what we're doing in monkeys is the thing that we can't quite yet do in humans, right? And we're switching to, we're focusing more and more on brain-controlled FES. So for these experiments, we inject a little bit of lidocaine near the nerves, and the monkeys just watch YouTube videos for the course of this experiment, and these are, my students controlling the hand, actually using the system from Case Western. All right, and so I want to make the argument that FES has a lot of room to expand. People think this is a very old technology. People have been doing this for decades now, but they've been doing it for decades now with a relatively small number of channels and, a small number of degrees of, being able to control that limb. So we want to go up dramatically in channel count and also like effective channel count, like how independent are the movements. Okay, so small dissection photo over here. This is a nerve. So what we're proposing, and this came about as another neurosurgery resident, Io, spent research time in the lab, and and was reading the literature on all of the different approaches for trying to get better FES. So the early FES that everybody thinks is as done as good as it can is intramuscular, where you're placing electrodes into the muscles or on top of the muscles. I think engineers really want to address this with a new electrode, right? And so but electrodes, even if they are perfect, they have a bit of a physics problem, right? If you're in the nerve. And the physics problem is that the things that you are trying to independently stimulate are, sometimes only a few hundred microns away from each other, right? And so current spreads, even if you somehow could, magically get in there without damaging it. And get into the right spot. So there's just this is very physically difficult. And so my resident said, okay, if you want the nerve branches so bad, why don't you just ask the surgeon to implant at the nerve branches? And I said, you guys can do that? And he said, yeah, in fact, this is really easy for us. We always have to know where these branches are so we don't damage them. So we're always trying to visualize them. And sorry, so what you're looking at here, this is a nerve, right? So you have these, 3 main nerves that are running down your arm, and they are throwing off branches into the different muscles as they go down. And these are referred to as motor points, right? It's the point where, a bundle of nerves, enters the muscle. And of course, it's still continuing to branch, et cetera, after that point. So the logic behind our surgery is we're going to take each one of these places where a nerve branches into the muscle, and we're going to drop a small intramuscular electrode a few millimeters away from that. And we're referring to this as direct motor point FES. And this is in the older literature. We've found this, but I don't think anybody's followed up on it since the early days. So, so we're starting to do this, and we're starting to get, we're certainly getting a lot of movement out of this. So you see a flexor supercut on the left and an extensor supercut on the right. This has been really challenging to quantify because we're now getting so many different weird movements that we can't just put bend sensors on all the joints. And so we have to reconstruct based on, video, and we're making great progress in markerless motion capture and deep lab cut and things like that. But it's still very difficult to quantify. And if it's difficult to quantify, it's also going to be very difficult to program. So this is our area of active research right now. Where I'm working with, so if you have a 8-channel system, there's, a small number of experts that can just tune the knobs of those electrodes and get functional movements out of it. But that is, by the time you have 32 channels, there might be more possible stim commands than the number of particles in the universe, right? So you're not going to want to train it like that. So I'm working with a new assistant professor, Ann Drelos, and the focus of her lab is very fast, statistically optimized searching. Right, and so what we're going to do is introduce adaptive search to programming these systems. And so we've done a 16-channel animal, and that went really, really well. And we'll probably, we're trying to go to 32 channels with that adaptive stimulation, which also requires that we have to motion capture the hand. So that's sort of, where my lab is today, what my students are doing right now. All right. So let me talk next about electrodes. I don't know how I'm doing on time. So everything that you saw for the brain-machine interfaces is done with the Utah array. And this is basically the only thing that has enabled high performance in human experiments also. And I always feel bad saying anything negative about the Utah array because this was developed in about 1999. And when in engineering do you have something that is so good that it stays the best performing device for 25 years? So, before I say terrible things about it, I just want to shout out to, Dick Norman and colleagues who got this working, for making something that has been the best thing we have for 25 years. Okay, however, you're seeing neurons recorded by a Utah array, and this is on, from our monkey that we got all that really great high performance BMI from. And this one has a neuron, this one has a neuron, this one has a neuron, but mostly what you're looking at is a field of black. And, it could be, there's definitely materials failures and biological failures, but there are failures, right? Like this is not unusual for a Utah array, and it's certainly not unusual for an older Utah array. All right, so we know that over time, scarring develops around these electrodes. And it's kind of different than people think. It's not that it's like, fading very, very slowly because of the scar. The scar is basically in place after 2 months, and you're seeing, every video you've ever seen has just been, this is what we got after scarring, right? But it is still getting worse very slowly for the materials and, potentially neurons moving and things like that. And if you go back in after several years, at least in monkeys, where we would expect it probably to be worse, more than half of the neurons are gone underneath the electrode array. All right, and in humans, to date, this is a rare opportunistic data set from someone who died of an unrelated condition while they had a Utah array implanted, and they saw very similar scarring in the human case. All right, so we're going to try to solve this problem with carbon fiber electrodes. So why carbon fibers? It's pretty much the same reason that you want to use carbon to make a better mountain bike, to make a better orthopedic implant, and to maybe build a space elevator. That's different carbon. Okay, so it's biocompatible, right? We are carbon-based life. So I don't just mean that this does no damage. This is the kind of material that you put on other things to make it more biocompatible. So, so starting point, pretty good material. It's chemically inert, and these are different problems, right, to solve, right? So it's got to be biocompatible so it doesn't damage the brain. But a lot of the problems we're seeing now is the brain damaging the electrodes, right? So we want it to be chemically inert, and carbon is basically immune to dissolution, right? So it's going to be able to stay in the body for long periods without dissolving. It also resists buckling and it resists fracture. So it's kind of a material that is abnormally strong for how well it does this, right? So these are carbon fibers, and I should mention these are 9-micron carbon fibers. So they are about the same size as a capillary. They're extremely, extremely small. And so let me play this video, and this is a glass capillary being rolled over the electrode arrays that I will show you in a second. There is no other material you can do this with, right? So if I did that to something like silicon or a glass electrode, it's going to break. If I did that to a metal electrode like platinum, it's just going to bend over and stay bent. You have to make sure absolutely nothing touches microwires of this size, whereas with carbon, it's, certainly we can break these, but they can be surgically handled in a way that they're pretty darn robust. Okay, and finally, they're conductive. So they are the electrode. And you can sort of, you can augment them by putting metal on the tip, but basically you have something where you're not worried about, tiny metal traces, dissolving or getting broken over time. Okay, and so these carbon fiber electrodes, provoke minimal immune response. So what you're seeing here is brain, and this is a rodent, and green dots here are neurons, and white dots are where the carbon fibers were implanted. And then down here is what healthy brain looks like. And so there is no significant difference in the number of neurons in the top image and the bottom image. You can detect that something's going on. You can see this blue and red is markers of inflammation. So I think of it as like, okay, there's like a ninja in their midst, but they can't quite see it. And, the neurons are staying in place. And so we looked at control brain, and if I just throw down a dot randomly in control brain in any spot that's not inside of a neuron, the closest neuron is an average of 16.2 microns away. If we take the centroid of a carbon fiber, the closest neuron is 17.2 microns away, right? And most of that distance is the diameter of the neuron, like getting to the centroid. So these have, very high yield. There's the caveat is that they're much harder to manufacture, but when you stick them in the brain, you are going to record a neuron. So, these are, and they also start working basically right away, which is really nice for example, intraoperative recording. So, when I say basically every neuron here, you're seeing an acute recording. So this is something where, we don't have to make the head cap last forever. But 97% yield at 100 microvolts or higher as a unit. And actually, 24% record 400 microvolts or higher single units. And chronically, the number we estimated is, above 80% yield, but we still think that's probably, the missing ones are probably our manufacturing. All right, so this is what it looks like. My student, Joe, he constructed from those histology images the actual position of neurons surrounding the implanted electrodes. And this is what they look like. They're really up close and personal with neuron cell bodies. Even at about 3 months after implant, when you would expect any scarring to have formed. And this is really, really important for recording high quality signals. So I think a number that you see tossed around in papers is maybe you can record for 50 microns or 100 microns away from the neuron. And if you're not recording from neurons, you're recording from larger and larger populations of neurons, and the information is getting less and less specific, right? So the 125,000 word speech decoding, you're going to need some neurons for that. And so we found that we matched the position of neurons and the size of the waveforms. And when we fit this, we find that the places where you can really sort out individual neurons are really more like the first 30 microns around the electrode, right? And after that, there's sort of, imagine like growing spheres, right? And the annulus of that. And there's more and more balls inside as you go away from the cell. And after about 30 microns, that's the point where you're probably not able to differentiate all of this out here. Because again, the shape of these waveforms, they vary a little, but they're not that different, right? So it's very hard to sort out. By the time you have, waveforms that differ by like a few microvolts from each other. All right, so let me say this is where I'm going to talk about some exciting unpublished work that I probably should not put on the online video. We're in the process of submitting this, but we just presented this at Society for Neuroscience. So up here is Jordan Lamp, who's also a neurosurgeon, and he did his residency research, and he was tasked with figuring out whether carbon fibers, which do a good job penetrating rat cortex, are actually going to work in larger brains, right? So we went to sheep, and we want to see, we know that the top layer of the brain is thicker in sheep, and we wanted to see if that works. And we know this only works if you sharpen the carbon fiber, right? That's the only way to get like a whole millimeter or a millimeter of half into the brain. And so some very zoomed in brain surgery pictures coming. Here's the carbon fibers down here. So there's a 10 by 10 array of carbon fibers. And you can see them, they're just going to start disappearing into the brain right there, right? And again, these are 9 microns. So they're capillary size. They're extremely, extremely small. And, to my knowledge, like there's no... The commercial systems, there's certainly no other electrodes that are close to this in size. Certainly there's other called ultra microelectrodes in the lab. But but you can't just stick, 100 of them in the brain by turning the screw on a microscope, right? That's what you get for carbon. You can see it coming out right there. So the project was just to see if this worked. But quickly we noticed, what we guessed at, but, it was much better than we thought. There's very, very little bleeding, right? And very, very little damage as a result, because we actually spaced these out further due to a project that I'll tell you about in a second. So we're now spacing them out at 400 microns apart, very different than our rat electrodes. And so what you see here is carbon fibers as an ex vivo sheep brain pictured next to a Utah array. And the volume of our electrodes is 98% less than the volume of a Utah array electrode. So very, very small. So again, we started observing that the brain looks unperturbed, right, after we put in a carbon fiber array. So our control, and again, it's great if you do engineering that lives long enough to be the control. So the control is always a Utah array. And there's always a big bead of blood, right, that comes out if you implant a Utah array and pull it out again. And there's a lot of papers and literature that suggests that this initial insult is, very related to the quality of the signals that you have 3 months later, right? So carbon fibers, quickly noticed that the capillaries appeared intact. And if we just look at this statistically, the reason that they're not hit, the biggest reason there's no bleeding is because an 8 micron thing on average doesn't hit anything, right? So, here you have a slice of vasculature from real brain images that, shows an 8 micron slice. And then over here is an 80 micron slice, which is probably, this is more like what a Utah array electrode encounters, and this is more like what a carbon fiber encounters. There's a further results, it's just on bioRxiv right now, but from Nick Malash's lab, that also suggests that things in this size scale, particularly if they're pointy, can't actually capture the vessel under it. So a capillary is still probably more likely to roll off. So on average, it's going to hit 1 or 2 capillaries. It's unclear if we're even breaking those. So of course, that's a statement that we really need to prove. Okay. So, here we're starting to have the histology roll in. We think the data set is complete and we're trying to make final figures for the paper. We're looking at bleeding here through epiillumination. So you can just see, this is a Utah array. This is all the spots of blood that happen as a result of the implant. Nothing for CFA. And then we also did Nguyen. And these are, Nguyen tells me about neurons. And we were surprised how much we could actually see doing Nguyen staining after an acute experiment. So this is after nothing but a Utah array impaction. And so there's a dead spot, right? Right where you have that electrode array. And carbon fibers, wherever we put carbon fibers, looks very close to healthy brain. Okay, so during the course of this project, Jordan, the neurosurgeon, was presenting this work at local department meetings, internal meetings, stuff like that. And he kept saying, "There's absolutely no bleeding. There's absolutely no bleeding." He's a very, very excitable person, right? And everybody was telling him to be more precise, right? We're like, you can't say 0. Probably there's bleeding. We just haven't seen it. You have to wait until we get our imaging back. All of that. So he got a little bit frustrated with us. And this is him in an acute experiment, and you're looking at a sheep brain right now. He put a 10 by 10 carbon fiber array into the brain 100 times. So this video is way sped up. But this is the brain afterwards, and it looks pretty good, right? So he drove the point home with the rest of us that, we should probably change the overall thrust of the paper. Right. So this is when you see this come out, it's going to focus much more on, the lack of bleeding and the lack of neuronal damage. All right. So my very last, slide here. Yes. I'm going to talk about, we were very fortunate to get a large grant from the Marcus Foundation to try to use carbon fibers to build a system where what our goal is to have 1,000 electrode implants be, safer to the brain than implanting 100 conventional electrodes, right? And we're working very closely with Jamie Henderson at Stanford. At Stanford, they're going to try to expand their current studies into Broca's aphasia, so people who can't speak after a stroke, even though it's very, very clear that they can think in words, right? They can answer questions and things like that, but they can't speak. So that's what they're doing at Stanford. And at Michigan, what we're doing is attaching tiny microchips to the back of these carbon fiber arrays so that we can implant them in much larger numbers. All right, and we're aware that this is a major packaging challenge. So what we've done so far is, these chips really exist. Prototypes have really been attempted. One thing we're doing from the project is we're getting away from sort of, student-made devices, right? For some of these pieces, we're starting to work with manufacturers. But we have sort of attempted fully integrated prototypes that almost worked. And we've done a lot of work building dummy devices and trying to figure out how we're going to handle them and implant them and things like that. So this is real silicon over here. This is just bits of silicon with carbon fibers put in them and sharpened. All right, and these absolutely, we have a procedure. It's up on bioRxiv at this point. We attach them to a device with something that can dissolve. It's a very biocompatible substance, and you just drive them into the brain. Flush some saline over the area, and you can leave them in the brain. And that is, and over the course of the next 5 years, so we're about half a year, maybe 3/4 of a year into this project, we are hoping to move to systems level large animal experiments within the first 3 years of the project, and then we are going to be trying to assemble a data set that is appropriate for the FDA, and try to move towards first in human experiments, around the time period of about 2030%. So that's the overall goal of the project. All right. So with that, I want to thank all of the people. I tried to put people's photos on their work because, I'm basically like a glorified publicist, right, for the awesome work done by my students and postdocs. The lab has a lot of people from biomedical engineering, electrical engineering, and robotics, and neurosurgery. So that's sort of our makeup. I also have wonderful lab alumni. About half of them have ended up at neurotech companies, and about half have gone to be in academia. And with that, I want to very much thank my funding sources. Marcus Foundation, I need to get the logo, but that's bolded at the bottom since they're funding a lot of our work going forward. So thank you very much, and I would be very happy to answer questions.
I have many questions, but I think I better ask the audience first. And whoever is tracking Zoom, if there is anybody online, maybe we can start with that.
There's no questions yet. We do have from Dr. Armand. Since LSTM performs sequential processing, do their computational efficiency create a problem for your applications? Can you comment on their performance and advantage, disadvantage compared to transformers or more simplified gated recurrent units for your application?
So I'm going to not try to remember the numbers, but the Costello et al. Paper has some, comparison on the computational complexity of that. And it does have like all of those different architectures. And also that paper has code available. So you can sort of actually see, you can run it and see how that works. So the overall question of the computational complexity. So I remember being part of very early neural network testing at Stanford around 2011 or so, and that was really taxing our systems, right? It was taking every millisecond of 50 milliseconds, right, to actually execute this neural network, and it was a real computational problem. That is no longer the case, right? So, a couple of things that happened since then. ReLUs, rectified linear units, really, really computationally efficient. It's not that much worse than running the linear algorithm. So the bottom line is, everything that we're running, we have a decent, real-time GPU system set up, but everything I showed you executes within a couple of milliseconds, right? Like file saving is a bigger problem for us, right, than running our neural networks within one of these control loops. Training is a different story, right? For that, you need minutes, right? And, but that's the difference between, experiments now and experiments, 10, 15 years ago is you just need minutes, right? So we actually have our monkeys watch YouTube videos. It's very important that your monkey doesn't get bored and, they get frustrated. So we put on their YouTube videos, which they like watching. And it takes about 5 minutes to retrain the algorithm. And then everything is able to execute in real time really well on a decent computer. There's a serious question about putting neural networks into implantable devices. So that is the point where, well, I don't think that's going to work. So I think we better, get the features off of the device. And so, so there's definitely reasons to think about computational complexity. Like this is still a very simple task, right? We're decoding 2 degrees of freedom. It's going to get worse, not better, right? As we start increasing the complexity of our tasks. But, it is one of those things where computers getting faster has made this work really well, right? And that's the biggest thing that's changed, since 2010 or so.
Next question.
Thank you so much for that wonderful talk. So a lot of what you have done over the years has focused on the brain-muscle interactions.
Yeah.
Again, with the end goal of controlling movement, right? So I was thinking of a different application. I just wanted to hear your thoughts on it. There's a lot of interest now in looking at the brain-gut connections.
Yeah.
So I was curious about how some of the lessons you have learned over the years can translate to, say, controlling peristaltic movement and eventually metabolism.
So I don't know. I mean, I suspect that, so if we develop all of these systems for neural recording to treat these sort of beachhead applications, severe paralysis, right? Things like that, our ability to record from the nervous system is going to get much, much better. And we're gonna realize it's been really bad so far, right? Like how many people have actually really recorded from like an intact vagus nerve, right? Which is going all throughout the body, innervating everything, doing all kinds of things. And so in brain-machine interfaces, it is magical, the things you can just read out of brain activity with half-competent machine learning, right? I think that's going to keep expanding, right? I think neural recording, it's going to start expanding for small medical applications and then hopefully start revealing more things, right? That where we can at least, use it to understand the mechanism, or, develop closed loop treatments, right? For example, for how many treatments are, is it just very hard to manage drug dosing, right? Or things like that. And if you had a really, really accurate, titration, would that be improved? So I'm not very familiar with gut brain in specifically, but I think that, by the magic of comorbid conditions, as the number of people with recording systems expands, I think we're going to start learning a lot more about what the nervous system does as it relates to a lot of different conditions. Yeah.
This is not my field, probably. My question is very naive, or maybe I should ask you 10 years later. How these neuroprosthetic hands could protect us against falling, because hip fracture, etc., among the adults is a huge issue. And compared to a standard, or is anybody thought about that? Is there any evidence that it could prevent, be protective when we fall down?
So let me answer the question of whether any of the neuroprostheses being considered are anywhere close to able-bodied. The answer to that is no, right? If you have a functioning hand or, functioning leg, the prosthesis, and even if you have, pretty severe nerve damage or things like that, you're still better off, right? Having, an existing limb. And it's because the robotics side is actually very limited. We kind of have we worked with some really amazing prostheses, but they are still nowhere near what, an able-bodied person can do. They don't have the same degrees of freedom. They don't have the same sort of, precise control structure with the sensation. And so it's very far from, any situation where you could use it to, where you'd imagine anybody being treated, with a prosthesis when there's, any way of saving, the existing, I would say. But, never say never in engineering, right? Again, this field barely existed 20 years ago. So, things are moving quickly. And I hope that we now have better control signals than we have prostheses to control, right? And so that I hope motivates, more advanced prostheses coming out in the next few years.
Thank you.
This is also a little bit outside my field of expertise, but in my field, something that we have been seeing is these systems are being like decentralized, right? Before we used to try to put all together into this big piece of, and now with wearable devices, we have seen more and more systems that are being centralized and distributed. So after looking at the array that you have, are there any plans to try to explore a similar approach where you can have like multiple implants around the body?
Yeah, absolutely. Yes. And that Case Western system is trying that concept. There's devices everywhere. The practical problem is that power delivery is very inefficient between those different devices. So if it can somehow be wireless or something like that, that would help a lot. But that is the dream, right? And also, from our project where we're trying to put individual electrodes on chips, we're trying to be able to distribute, as far as we can go. There's also the question of, where to put the computation, where to put like all these different parts of the system. And the cool thing about brain-machine interfaces is that the actual feature we're getting out is a relatively small amount of data. So I hit the last slide at the end there because it was, too much to explain, but you can do 1,000 channels in a couple of megabits. Right. And so it's not that high. And so what that means is that, we're not really considering putting like compute of the algorithms in the device. We're just getting it out of there. Right. And, we think we can do that in a fairly low power way. And it's because, the recording of traditional electrophysiology, that's a very high bandwidth, high data kind of thing. The actual features that we use, they're tens of milliseconds tops, like per time. And we know the number that we want, right? So some of these implantable systems have power modes that are extremely efficient, right, for getting this feature out. And no one is yet looking at, putting the algorithm on there because you might as well have it on, whatever you have extra on that system.
Good. I was going to ask, how do they actually manufacture the carbon fiber for this application?
So really good question. So it's a burning process, right? And I won't embarrass myself by pretending to know the details. But they start with some kind of starter polymer and they burn it. But we've been really impressed by how consistent the sizes are. Right. The, precise dimension within like, 0.1 microns or whatever is okay for us, but they've been pretty standard when we buy, these rolls of carbon fibers. So compared to other electrodes that are being made in clean rooms or manufactured in other ways, these are basically free. Right? Like anyone in this room could go get a roll of the carbon fibers that we're using. In the words of my colleagues, this is literally the stuff in your tennis racket. Right. So, we're never going to run out of any roll of carbon fiber we have ever bought. So, that part is easy. The hard part is attaching to something, right, and manufacturing. And so, there we're looking at a lot of solutions. They can absolutely be made laboriously by hand. Right. And that's everything we've ever done to date. But I know this, scares off a lot of companies. Right. And trying to think about how to bring this to humans. So, one of the things we're really focused on is, if not fully automating the manufacturing, just showing what it's going to look like with a, pretty, a optimized process for me. So, yeah.
Couple questions, maybe we can get to both of them, but one is about this carbon fiber, and so you showed how bendable it was.
Yeah.
Seems, well, great for survival of the electrode. I was wondering if you have any information about what that means for the long-term recording capabilities in the brain, and not so much in terms of scarring, but in terms of movement.
In terms of movement.
And so
okay, so what we have to date is rat data for up to 3 months, and it's pretty stable, but that's also a very short, right, in terms of neurons near the electrodes. I don't know, my totally utterly unsupported hypothesis based on Kristen Welly's papers is that what you're sort of seeing over long terms is more general neural degradation, neurons going away, neurons remodeling away, and that's sort of what you're seeing on these time scales, not so much like that initial sort of scarring process. And so I'm hoping that as we start, longer recordings with carbon fibers, that it keeps looking as good as the free market, right? By having an electrode in there for a long time.
So now you're getting, I guess, because of the bendability, I could imagine that you kind of move with the brain as things, but you're able to penetrate, and so as the brain moves longitudinally, or your electrode moves longitudinally relative to the brain, you might get very good, strong movement there.
So
how are you floating how are you floating the array?
So right now, so if we stick this on if we make a carbon fiber Utah array, right, then we are going to have a base for which the forces from one electrode can go to the other electrodes. We're hoping that when we do it like this, right, things are a little better, right? So when I play these videos, you can see they're basically going in straight, but there's slight angles, right, for each of the carbon fibers. When you release the motes, you see them all make a slight adjustment, and they end up in this all slightly different, directions going forward. And that's a response to that force stress, right? Where they're just relieving their force individually, right? And
the idea here is those are each individually floating.
Yes, absolutely. Yeah, and so they cling together just because we thought it was going to be really hard to make these, but they love grabbing onto each other due to surface tension. So you have to prevent this. Otherwise, they will tend to glom together on an insertion tool and make themselves look very much like a Utah. So,
okay,
Great.
go ahead.
No, thank you.
Yeah.
Last question, short.
Yeah.
So, question about the nanofibers. So, obviously using it for recording electrical signals.
Yeah.
Have you also thought about attaching
STEM?
probes to it to detect cell surface biomarkers?
Yeah. This is the same carbon fiber that everybody uses for that kind of thing. So the average lab, there's carbon fibers all over neuroscience labs, but they're all for neurotransmitter sensing, right? And then they functionalize, you can get dopamine with bare carbon, and then you functionalize the surface to do other things. Carbon fibers are great whenever you need something that needs to land very, very close to its target and stay there for a very long time. Back from the 80s and 90s, people have told me that this is the only way they were able to do spinal cord recording, right? Because it does very little damage and it's going to stay close to what you want. And anything that you can attach to a carbon surface, right, you could absolutely put on these probes, right?
So do you have time to talk afterwards, but we officially close the seminar time right now? Absolutely fantastic. Gorgeous, wonderful to have you here. Thank you for also all the engagement with everybody.